All right, shall we get this thing started? I hear people here liked Kafka. All right, as with all of these things, I've got to give a forward-looking statements disclosure. Please only base your decisions on what Salesforce has publicly announced already. Everything else, we leave to your imagination. Greetings. We're going to talk about a bunch of things today, primarily what it means to build event-driven systems to cope with this world of events that's emerging around us. We're going to talk about Apache Kafka as a primitive and abstraction for dealing with those things. We're going to talk about how to tie it all together on Heroku. I work at Heroku. It's a great part of Salesforce. I'm director of product management over there. I work on everything big data, streaming data, machine learning, data science. We're going to go through a lot of different topics here, everything from how we got to this place where events are driving all of our architectural decisions. We're going to talk about what events are in detail, what event streams might be, what Apache Kafka is and why it's rising in prominence in most of the big data stacks we've seen. And we're going to talk about how it ties together with all of the awesome capabilities of the platform as a service that we've got in the app cloud known as Heroku. And at the end, we're going to get to some questions and answers. And I've heard that this crowd has a lot of really interesting things to dig into in Kafka, so I'm looking forward to getting there. All right, let's see if we can get this thing forward. There we go. All right, a couple questions to start things off. Who here is actually familiar with Kafka? All right, pretty good group of the room. Other event streaming platforms? Great, we'll dig into those a little bit. Who's here familiar with Heroku and the rest of the app cloud? This is awesome. That's such a huge change since 2 or 3 years ago. Are you currently faced with architectural scaling challenges that are forcing you to actually look at Kafka or other event-driven systems? Okay, so a lot of curiosity, some scaling engagement taking us there. Are you currently considering other event-driven systems or have those in your topologies already? Cool. So a lot of people looking at the space with fresh eyes. That'll be awesome. All right, so as it said on the headline, we live in a world of events. What does that mean? We hear that from Salesforce, we hear that from Heroku, we hear that in all of the big data tech mags. There are a lot of things going on here. What exactly does that mean? So the ecosystem has changed over the last several years. Not only are products hitting scale so much faster, you can deploy a mobile app and it will hit hundreds of thousands to millions of customers overnight. You've got microservices on the back end. This isn't necessarily your client applications, but all of the constituent elements of your product stack are talking to each other. You've got intelligence. As we saw with some of the earlier keynotes on Einstein, we're deriving a lot of intelligence from our data. And that means the systems have to get the right data in the right place at the right time in the right format to do something useful with it. And we've also got the ascendant world of mobile and the Internet of Things. So we've got all of these devices creating all of this output, pumping it onto the network, and we've got to do something with it. So here we are, we're swimming in events. Why is that problematic? Well, we're going to take a look at 3 specific cases that we've been wrestling with as sort of high-value abstractions in our stack over the years. Inbound streams, so that's pulling in this massive flood of events from IoT or distributed clients or mobile apps. Data pipelines, where you're doing either streaming ETL, data enrichment, log aggregation, processing, et cetera, and microservices. We've got a lot of things on the back end that want to talk to each other. How do we help them find each other, communicate, and do so reliably and in a low overhead manner? All right, so the way we've been doing that historically have been through either transactional interactions or remote procedure calls. And I know the crowd here is fairly technical, so just in brief, transactions, you've got a lot of ACID semantics for atomicity and consistency, isolation, and durability. Essentially, you've got a lock over the mutation of the data. Remote procedure calls, this is usually service-to-service interaction that drives a synchronous change, sometimes asynchronous in the more modern stacks, but really point-to-point interaction. So why is that painful in these scenarios? With your inbound event streams, you've got an extraordinarily volatile load coming in from outside of your platform. And as that comes in, you have to be able to react to that push. You essentially have to be able to scale in a wildly volatile manner the accepting pipeline of events or of services that are backing that API endpoint. This can be really problematic. One, if you overscale to handle that load, you're going to be really inefficient. Two, if you need to be able to handle back pressure, that requires a lot of intensive coordination amongst your systems, and you might not be able to bring it to play fast enough. And if you don't handle all those cases, you're going to drop data. And if that's important to your business, you've lost a lot of value. Data pipelines are another case that we see all the time. And again, I mentioned this would be like streaming ETL, log aggregation, analytics, coordination amongst distributed systems, et cetera. And this has some similar problems, but with some great nuance. So if you've got data going from point to point, and system A is sending to system B, and system B is not up yet because it's restarting, or there's a network fault, or whatever, you've dropped your message, or you have to go through complex retry logic. This can be, again, expensive and difficult to coordinate, especially on the fly with large systems. Also, if you've got a lot of consumption of data as it passes through the system, i.e. goes from system A to system B, but it's not available anywhere else, you've essentially performed a destructive or mutable transition on your data. And that inhibits your ability to do parallel processing of the same data unless you jump through some fairly complicated hoops. And we're also moving into a world where there's a lot more provenance and accountability issues or auditability, whether you've got SOX compliance or PCI compliance or HIPAA compliance or other things that a lot of our world deals with. If you want to be able to backtrack to what all of your data was and how it got to the form it is and to the systems that it's now resident in, a lot of these point-to-point data pipelines fall pretty short. And microservices. This is sort of the de rigueur way of building scalable systems these days. There's a lot of debate about that. We won't get into that. We'll save that for Vim and Emacs later. But having all of these things, again, talk one to the other can be a little bit problematic. You need a service discovery system. You need to have the same sequencing, service A being up before service B is up. And again, you have the possibility of losing messages on the wire between systems. Sort of complicated, a lot of overhead, but everyone's doing it. So what do we do about it? Well, we have this world of events. And events essentially liberate us in a lot of ways from these synchronous locking interactions between systems, whether they be transactional or RPC. All right, so what is an event? We throw this word around a lot. I'm gonna get a little pedantic. Bear with me, it's my way. An event is a contextualized operation on state. So when I say contextualized, it's got the context of what device produced it, when it produced it, was there causal history behind it? What's the geolocation? What's the time? Is there a vector clock associated with it? The operation is important too. It's not just that an event happened, it's usually state and a function. So was it a create, update, delete, modification, et cetera? It's an important thing to embody in your event. Also, again, the state itself, the payload, how it's defined, how it's named in the system. So that's basic definition of event. What is an event stream? Well, in theory, they are immutable streams of events where each event is an immutable record of a transition in state and context. String these things together in big unbundled streams, and you can eventually get consistency by replaying that, evaluating them, and understanding what happened. But being able to do that depends on a lot of things. There are a lot of asterisks at the bottom of this slide, so you've got to think about your ordering, whether that's unordered, total ordered, partially ordered. You've got to think about your delivery semantics, whether that's best effort at least once or exactly once. And those asterisks are sort of important because a lot of them actually have limitations in the world of math and physics. Ordering is really complex. You can never really have more than partial order. Even if you're using time as your ordering construct, you might have two different NTP servers that your devices are talking to or different clocks on the back end, and you'll have all sorts of temporal skew. Even if you get into causal history, it can be a little funky to resolve. Exactly once, you'll hear that a lot in a lot of streaming presentations. It's a great thing to aim for, but again, impossible. Every time you send an ACK over the wire saying, yes, I got this exactly once, the ACK itself might get lost. So you've got this sort of recursive Zeno's paradox like rabbit hole into the madness of time. So, all right, now we've got events. There are also some trade-offs that we have to think about when we're going to build systems on top of them. Quoting Heinlein, right, so no such thing as a free lunch. We don't get ACID compliance or ACID, atomic, consistent, independent, and durable rights with these things because we don't lock a transaction. We also don't have any complex reach into a schema of the data being modified. So when we think about how to build these things, we've got to think about, are our events idempotent? Can we send them and apply them more than once safely? Are they commutative and associative so that we can apply them out of order? Because some network pathways are going to be faster than others. Also, are there out-of-stream processing elements that we need to account for? Joins, whether those be streaming joins or static joins, et cetera. Happily, we can leverage some of the contextual state that we've got on those events to rectify some of these situations, but there's a lot to deal with here. But they are valuable, so we want to do this. So event streams in practice. In order to make use of all of these capabilities and in order to mitigate some of the trade-offs, we have to think about moving these things fast, because the whole point of events is to help us scale. So we need high throughput, we need to be able to handle failure, and we need some structure to be able to mitigate all the trade-offs. All of those needs come together in a fairly nice way with some similar solutions, or self-similar at least. One is parallelism. Parallelism gives us some nice constructs for fault tolerance and increased throughput, because we can spread out and distribute the load, have multiple runways. Also, stream structuring is really important, whether that be namespacing or partitioning, to give us some sort of semantic sense of how the data lives within our event streams and where to access it. So it's not just some big undifferentiated temporal soup. That's for data lakes. All right, if only we had a pragmatic solution to all of that. We do. It's Apache Kafka. There are other solutions out there, but this is certainly the leader in the space. It's a great bundling of all of these abstractions and complexities underneath a really nice development environment to deal with immutable event streams in a fault-tolerant, resilient, robust way. So the core elements of Apache Kafka. There's some fun little keywords here that are a little bit different than they're used in the rest of the ecosystem, so worth noting. A broker is essentially an instance in a Kafka cluster. It's one of the members of that cluster and upon which all of the data is distributed. Producers and consumers are the sources and sinks outside of your Kafka cluster that are producing and consuming the data. Topics are analogous to your streams or table spaces. They're the high-level naming construct of your events flowing through Kafka. And partitions are discrete subsequences of topics and sort of form the fulcrum around which you can tune your parallelism and semantic structuring for your data. All right, one of the other things that we often hear Kafka called is a distributed commit log. Sure, it's a messaging system, it's a streaming system. This is the most pedantic and true answer, therefore it's very near and dear to my heart. What does that mean? It's a stream of immutable events. It is commit only in a distributed fashion. So immutable events are always written to the endpoints or most recent entries on your partitions, which are again the subsequences of your topics, and those stream forward forever into time. They are, again, append only and distributed and replicated, so everything is written to a leader of a partition and then replicated to the in-sync replicas across the cluster. This will be a little bit important for thinking about how we model event streams for our business cases. All right, so we've been talking about events. In Kafka land, these things are called messages. That big crazy thing on the side there is the sketch of the message format. We don't have to worry about all of that right now. It's worth noting that there are some high-level attributes to messages that are really important, again, for us to think about. One is the offset, which is the ordinal position of a message or event in a partition. It tells us where we are in history. You can associate optional keys with a message. Those can be based on anything. So like if you had an org ID or a user ID or a timestamp, those could be used as keys or compound keys upon your messages. Also, there's in Kafka.10 and up, which is a relatively new release, you have timestamps, and those can be, if you're looking very closely at the definition over there, either event time or receipt time. So what that means is you can encode from your producer or consumer when that event happened and pass it through, or you can let Kafka assign it a timestamp when it receives it. That's really important for being able to do out-of-order processing, rolling windows, sessionization, things like that. So really nice addition to the stack. When we step back up that level of abstraction, we've got all these messages going into our topics. Topics have some characteristics that are vastly different from tables, but that also bring them closer to tables. So your basic topic configuration is that of a time-based retention topic. So you're going to write messages into it, they're going to stick around for the retention window, and then be tombstoned and collected. Pretty easy, everything's always written to the end. Every event goes in there, even if you write things more than once, doesn't matter. Compacted topics are the other mode, and these are less often used, but an extraordinarily powerful tool. They are mutually exclusive, though. You cannot have a time-based retention topic that is also compacted. The key affordance of a compacted topic is that it will retain the last message of any given key. So if you write key 7 twice, it's going to tombstone the old key 7 and keep the newest value. That's a great way to create sort of a arrayified view of a table. It's one of the reasons that JCreps always says that events and tables are dual. They are sort of categorically dual when you do an evaluation over time, especially using this sort of form. You also have the replication factor. So as I mentioned earlier, you've got things replicated and distributed across your brokers. This is where you set that. It's on the topic level as opposed to the partition level. Partitions fall out underneath that. And that gives you the level of replication and resilience across your cluster, which is great for fault tolerance and safety. Best practice is usually 3 modulo the network environment you're on. So if you've got certain network environments, you want to push that up a little bit higher so you can deal with failure. But happily, Heroku handles most of that for you. All right, so basic message distribution as you're flowing things through Kafka. The most naive way to do it, and the thing that most producers will do out of the box, is to take a hash of your message and spread that out across your partitions in an even way to give you balanced load and distribution throughout your topic, which is great if you have a relatively undifferentiated message space and you don't care too much about ordering. Why? Because ordering is only guaranteed at the partition level. Because we always write to the head of a partition, the ordering semantics and the offset regularity is only guaranteed at that level. So what does that mean? That means that we might want to structure our event streams to fit into that space to give us guarantees around our ordering. One of the nice things that you can do is, again, using those optional keys on your messages, write a partition function in your producers to say, great, given a hash of user ID or user ID and timestamp, I'm going to send that to a consistent partition within the function so that when I'm reading off it later, I can make sure that those are always guaranteed to be in order and that I achieve the right level of parallelism across those entities in my application domain. There's a couple levers to pull when you're designing the number of partitions as well. You could say, oh, I just could have tons of partitions and have like 1 partition per customer and always make sure that everything's in order that way. There's some trade-offs there as well. Again, partitioning is going to be your level of ordering guarantee. So if you partition 2 in a too exaggerated manner, you can't really get great comparison amongst events because they're going to be in different timescales. Likewise, opening a ton of partitions is going to open file descriptors on the system. It's going to create more overhead during leader election and a bunch of other nuances that you probably don't want to have to deal with. Though, having more partitions does give you better parallelism because you're spreading things out, and it also, as we'll see a little bit later, gives you a better chance to do parallelization through consumer groups, which we're getting to now. So you've got all this data, you've modeled it, you've structured it into your streams, you're writing it at high speed into your Kafka cluster, and you want to get it out. You've got a couple of key ways to do this. On the first hand, you've got your basic primitive, which is the simple consumer. This is essentially any process using the Kafka client library. You can assign it to as many partitions or topics as you want, and it's going to consume off of them as soon as new events are ready, as fast as that process can, which is great. You can scale those things relatively easily by scaling them vertically, giving that process more resources. But let's say you want to go further than you can throw vertical scaling at. You want to actually get horizontal scaling at your consumption from your topics. Kafka's got a great concept called consumer groups for this, where you can register a number of consumers in parallel, and Kafka will say, great, here's how we can broadcast all of the offsets for all of the topics that you're reading from and all the partitions you're reading from, so that you can parallelize out to the number of partitions that you've got in a topic within one group and have each of them claim 1 partition and read as fast as it can from it. And they will coordinate among offsets so that it never processes something more than once. Yes, there are failure cases, but they're extremely rare in this case because there is a coordination unlocking mechanism that's local. And that gives you a lot of flexibility. So you've got a totally flexible primitive that you can do anything you want with, and then you've got a slightly more constrained primitive that gives you great parallelization and ability to run high throughput through your streams. So producers and consumers give us a lot of flexibility. Because we've got immutable event streams under the hood, we can have our consumers and producers fail and come back up and always reconnect from the last offset that they either produced to or consumed from, and sort of not miss a beat in terms of pushing things through our event streams. There are a lot of more complex pieces under the hood. There's setting up the OS underneath. There's tuning the JVM concretely. There is managing the Zookeeper cluster. There's a whole other cluster of services associated with your Kafka cluster that does a lot of leadership election, consensus, atomic broadcast, and a lot of other work in terms of making sure that things remain consistent. And then there's all the networking and resources associated with it. That's non-trivial. We don't want you to have to deal with that. So again, Heroku does that for you. So let's bounce back to those 3 specific cases we talked about: inbound streams, or as our CEO likes to call them, elastic queues, also data pipelines, and microservices. This is what they looked like in our old world, where we had to handle sort of erratic flow of events through the system. Here's what they might look like with Kafka as a backing affordance. Let's walk through them one by one. I'll be fast. All right, so in our inbound event stream, we had this big rush of events coming in. We had to react to things being pushed to us, and we had to react to this volatile scaling. When we move to the world of Kafka, we can take an initial process, and that initial process will still have to scale in a relatively volatile manner, but that initial process doesn't have to do much. It just has to accept the event, do some validation, and apply the partition logic to drive it to various topics and partitions within the system. From there on out, we can be pull instead of push, and add a lot of sense and reasonability and efficiency and scaling to our downstream system, because we've pushed all of that back pressure, all of that elasticity into our streaming affordance, which in this case is Kafka, as opposed to having to bake it into each independent layer of our service or application tier. Data pipelines. Again, we had problems with various stages requiring coordination, with lossiness, with parallelization problems, and provenance and accountability. If we are sending messages not from one system or service to the next, but through Kafka by dedicated topics and partitions, we know where that data is at all times. We no longer have to worry about whether or not a service is up or down, and we can always rest assured that the immutable form, the original form of that data, exists back in Kafka, even if we've done a subsequent transformation in a complex topology of processing. And finally, with microservices, which again, all the rage, and a lot of people like to use RPC for this, but I'm still a little confused about why. I get that. Like, there's a little bit of additional latency overhead when you're pushing through a secondary system, so we don't need to argue that here. But microservices through Kafka simplify a lot of things for you and maybe worth that latency hit, which is very, very small. You only need to know where Kafka is, and you really only even need to know where one topic in Kafka is to bootstrap your system. You can connect to a topic that knows the definitions of every other service in which topics they're reading to and writing from. So a service comes online, reads from this topic, bootstraps that, and knows which topics it needs to listen to or talk to in order to talk to the rest of the stack. It's great. And services can come up or down and not miss messages and be able to replay. So you've added a lot of stability and removed a lot of service discovery overhead. Gives you a really nice inter-process communication system. There's a lot of other things you can do with Kafka, and a lot of people actually do these things at high volume in production, both on Heroku and elsewhere in the wild. We've seen a lot of people do replay and simulation when you want to do parallelized testing of complex data environments. We've seen people unify tabular and stream data to do table stream joins, table joins, stream joins in their analytical processes. And we've also seen a lot of low latency stream processing, which Heroku is a great platform for. Also, when you're tying together a really broad array of system components, having one common backend against which to integrate is a really nice solution. All right, so Heroku ties all this together. And as a reminder for those very few people in the audience who didn't know what Heroku was, we're the open source friendly part of the app cloud. We're platform as a service, sort of pioneered that concept in the space. We offer a world-class development experience and operational experience, and we can support most of the languages that you would be using out in the wild. And that's pretty much everything not Apex or Force you can run on Heroku. We also offer really nice deep integration with your Salesforce data so that you can leverage all of that and reap a lot of those benefits. So this is sort of a vast simplification. Heroku ties together a lot of great flexible primitives for compute, for data, for workflow management, for orchestration, for auto-scaling, for CI, for CD, for integration with your Salesforce. But tying this all together in a really flexible, high-speed way, Kafka lives at the heart of that. And we do that with a lot of ease for our customers. We've given people a really nice dashboard that gives developers of all levels of experience with Kafka a great set of tools for managing, configuring, and understanding their event streams. So we've got industry-leading analytics and metrics populated there. We've got really great CLI tools so you can automate your interaction with the system. And we make it really easy to automatically propagate all the configuration that you need so that you can automatically plug this into the rest of your application stack. Heroku in depth, we offer a lot of automated operations. We make sure that things like Kafka are self-healing, that they're always up to date, they're always in the best configuration. We make sure that things are safely running, all the security patches and new versions are rolled out seamlessly behind the hood. You don't have to worry about downtime there. We'll auto-reconverge around system failure, and we'll provide you a nice set of alerts and recommendations when we see you doing things that are a little outside of Kafka's safe operating zone. All right, so let's see this in action. Some of our esteemed colleagues have created some nice little demo apps with this thing. Goodness, it's scaled my resolution funny. Well, but that's fine. So let's see if we can refresh that and have it scale back. One of the things that we've done is essentially created a demonstration application that pulls from the Twitter firehose for a nice safe set of terms and runs it through a data processing topology that gives us some visibility into how we can use, this web page is dead. That's okay, I will talk you through the logical flow, because that's perhaps more interesting anyway. So what this is doing is pulling from the Twitter firehose with a simple process that runs just as a Heroku dyno. That's the raw feed of all the terms we're looking for. We then have another process which serves as both consumer, pulling from that raw feed, and producer, doing a fan out, saying for each term, we're going to push it into its own independent topic. And this is all immutable, so we can do more things with that again later if we choose. Then we have two different consumers working in parallel on that same data without being destructive to each other. We've got one that's doing term count over time, so it's taking a rolling window of aggregated terms and then writing those to a compacted topic. So we've got a nice time-based key on that compacted topic, which we're auto-updating and populating with the count over time. So it gives us a nice table-like view there. The other one's doing some natural language processing to find all the related terms, and again, writing that out to a compacted topic to give us the count and term frequency for those things, and then consolidating those all into a raw topic to push off to a really light web front end. And this is sort of a trivial example, but it was super easy to set up a handful of dynos to do really complex stream processing and to give us a stable data source against which we could do more complex things in the future if we wanted to. So we do a lot more at Heroku than just make funny tweet visualizers too. So we use this all the way down the stack. We use this for our API event stream. We build Heroku on Heroku for Heroku and its customers. So all the API events, whether you send them from the dashboard or the CLI or internal tooling talking to each other, all gets populated and flows through Kafka. We also drive all of our metrics aggregation and processing. So if you have ever used a Heroku app and you know your metrics screen, you see your latency, your throughput, your CPU utilization, your memory utilization, all of these things as real-time time series analysis. Every app on Heroku, every dyno is pushing that through one Kafka cluster on the back end, and we're doing real-time stream processing on that. And one Kafka cluster can handle that without breaking a sweat, which is nice. So there's a lot more to learn about Kafka. There's a lot that's detailed in our launch blog post that went up a couple weeks ago. And there's also a lot of information up on our product page and in the Dev Center. And we've also got a number of great experts hanging out at the booth downstairs, wrangling a lot of awesome information about how we're using it internally and how our customers are using it and offering some best practices and tooling. And on that, I'd love to open it up for questions, and thank you for your patience as I ramble through Kafka.
Is the producer and the consumer of Kafka, is it bulkified? I mean, can somebody send multiple messages at a time, and maybe a consumer which is dead for some time and wakes up, can consume multiple messages?
So they can send and consume. You can configure producers and consumers to operate in batch, where they can send batches as opposed to independent events. And if that is optimized for your use case and reduces the system load on that service, yeah, that works just fine. Cool. I think we got one over here.
how long do you generally let the messages live?
Pardon?
How long do you usually let the messages live? Like for replay, for example, I've had like some conversations and there's like mixed message about get it off, let it just live the minimal amount of time possible versus let it just live forever.
So again, you've got time-based retention topics and compacted topics. Compacted topics are going to have indefinite retention for a bound key space, but they're sort of the specialized case. Most topics are going to be time-based retention, where you explicitly set the retention period for events in that topic. And we have a minimum retention of 24 hours and a maximum retention of either 2 weeks or 6 weeks, depending on the cluster that you're working with. And you can configure anything in between there to suit your business needs. A lot of people only need to keep them around for several hours to make sure that they've got essentially resilience in their system and auditability. Other people need to keep them around for several weeks so that they can do historical analyses of the stream in total.
So configuring Kafka is a pain. Does Heroku simplify that by having some pre-built configurations in there?
Yes, we do. So we have pre-configured the system to be the safest and fastest for the majority of use cases that we've seen and offer a lot of pre-configuration and some guardrails to keep you from getting it in a bad state. We also offer some simplified tooling via the dashboard and CLI to make changing parameters a lot easier. We know that running Kafka and its Zookeeper cluster and all of the associated pieces can be extremely painful, which is one of the reasons we thought it would be really high value to offer a managed solution.
Thank you. Then I have a follow-up question. We have a private Paas in which we use Cloud Foundry. Is there a differentiator between Heroku and Cloud Foundry when it comes to Kafka? Or are they similar?
So the Heroku platform is going to offer a lot of differentiation with Cloud Foundry. In terms of Kafka in particular, we have several Kafka core committers on the Heroku team, and we work really closely with that community to make sure that we have sort of the best and most up-to-date configuration, and that we've orchestrated extremely well for resilience given how our dynos operate around it. I can't speak in depth to how Cloud Foundry manages theirs under the hood. So.
Thank you. No, I appreciate that.
So it sounds like the Heroku add-on will make it really easy to get this set up and running in production. How do you recommend local development to work so that you don't have to worry about that complex configuration?
Yeah, for local development, I typically spin up a very small Docker cluster. And it has to be very small because most local machines would have their RAM exhausted by more than one Kafka instance and more than one Zookeeper instance. So I usually dial it down to about a gig of RAM per and run a 2 and 2 of Kafka and Zookeeper and use that for my local development. And there's some information on doing that with our recommended tooling in the development center. So.
Yeah, so the question is on the consumption side. So who is responsible for maintaining state? Is it maintained at the Kafka layer, or the consumer is supposed to maintain the state of what has been read and for how long?
So most of the recent, and by recent I mean later than Kafka 0.8, most of the clients past that mark in the history have utilized committing offsets to Kafka itself. So your consumer will read off and then in a configurable way, either once it's read or once it's processed, write the offset that it has just processed back to Kafka in a compacted topic. And that's the way that that state is maintained. So you usually don't have to worry about it locally, though some people do also like to write the offset to a secondary store so they can do external coordination. But you don't need to. It's all handled within Kafka if you use up-to-date client libraries.
Another question. In terms of, and this is just for my understanding, so is there any limit on the size of your message, or does that go hand in hand with your partitioning configuration? There
are definitely pragmatic limits to the size of the message, and that can be configured on the Kafka level. We typically recommend not sending messages larger than several megabytes. At that point, it's more content and maybe not as appropriate for an independent event. So an event might be a reference to that data at that point. I have seen people pass things in the tens of megabytes, but at that point, it's again, uncertain if the domain is right.
This is mainly a Kafka question. Let me know if I misunderstood this. You mentioned that in-order delivery is only guaranteed if we read it from a specific partition for a message, right? Is that correct understanding? Or?
If I heard that correctly, the ordering is only guaranteed at the partition level?
Yes,
that's correct.
So how do you, so does that mean that the reads always have to go to that same partition?
No, not necessarily. So reads will always go to the leader of that partition, though that partition will be replicated and you can fall back to followers if that leader fails. So really, you can parallelize up to, I mean, we've benchmarked up to 1.5 million reads a second with ordering guaranteed on one of our clusters. So the bottleneck's not huge, it just comes down to how you structure your events.
Thanks.
One more?
You were saying 1.5 million per second, right?
Mm-hmm.
That's the event inbound rate?
Yeah, so we've
how big
benchmarked
a
some of our clusters at 1.5 million events a second from being produced to being consumed back off,
Oh, all the way through.
end to end.
Did you have any challenges moving to a multi-data center environment, clustering across data centers?
So there are a number of tools for doing that, and it sort of depends on how we draw the boundary of data center. For clearly partitioned data centers, there are a number of affordances within the Kafka ecosystem that make that a fair amount easier. One is Mirror Maker, which is part of the primary Kafka distribution, which does essentially cross-environment replication of distinct topics or partitions in a streaming manner and maintains the offset integrity, so things maintained in the same order. There are other affordances that are more recent called Kafka Connect, which is a pattern of libraries that handles sources and sinks streaming for a wide variety of data stores, with at least one of them always being Kafka, but you can have both of them be Kafka if you'd like. And that gives you a nice scalable worker pool to handle that sort of bidirectional replication. Any other questions that I can help with? Awesome. Well, thank you all. It's been a pleasure, and thanks for putting up with me.